Okay, everyone, let's get going on lecture 20. The quarter is disappearing very fast indeed. So today we're going to talk about ice cores, which is a really exciting, fun topic. And we have a lot of researchers in our department working on ice cores. And we're going to look at why they're so significant and why they're so helpful to us. As a reminder, quiz 8 will be available from 3:30 today until 2 p.m. Monday as usual. So do continue to sort of see how you're doing with those quizzes. Okay. So what are we going to do today? We're really going to look at what in particular in ice cores do we study. So we talked already very sort of early on in the course, it feels a very long time ago now, about how we can look at the bubbles in the ice, and that in particular has given us our record of carbon dioxide concentrations for maybe the past 800,000 years, which is pretty spectacular. But we can also find out about a number of other things from our ice cores. So we're going to look at how exactly we get at temperature records, because that's the power of these things. They really demonstrate so nicely the link between carbon dioxide and temperature. So we're going to take a look at that. And it's a little bit complicated, but I have faith that you can do it. And then we're also going to look at the sort of the atmospheric particles that get trapped in the ice and what that can also tell us about climate. And then lastly, we're going to take a look at some of these amazing records and look for patterns and sort of have a look at a quick example of one of the things that we have learnt or that surprised us about our past climate. So first of all, let's think about what is involved in taking ice cores. So for those of you that were here a little earlier, you saw the video I had on the front where they were just taking ice cores from the top of a mountain glacier. But still, in terms of the logistics of doing this, it's quite a challenge. You have to get everyone, including all your equipment and storage, up to the top. And so often that's sort of people carrying it or helicopters. And we use pretty specialized equipment to drill these ice cores. So we want them to be pristine. We don't want them to get dirty as we drill. And we then sort of carefully package our cores and sort of keep them at really low temperatures, because what we don't want is to have spent all this effort going up to the top of this glacier, drilling this ice, and then for it to melt as we carry it down the hill. And as that melts as well, it also changes the chemistry of the ice. So we don't want that to happen. And then that ice gets transported around the world using special containers to where we can get samples. But first of all, we have to choose a location. How are we going to choose a location? Where would you go and take your ice cores? The poles? Why? There's ice there. It's a good idea to take an ice core where there is some ice. And what specifically about the poles might make it an interesting place to go and take an ice core? It stays there longer, so we can get really nice long records if we go and take ice cores near the poles. But we can also go and take ice cores in other places as well. If you were going to go and take an ice core, would you take it in the middle of the ice sheet or at the edges? In the middle, why? Why would you take it in the middle? Oh, is it Friday? No one can think on a Friday. Well, it's probably thickest in the middle, right? It's probably sort of hanging around there. Also, what do you think will happen to the movement of the ice in the middle compared to the movement of ice at the edge? Will there be more at the edge or more in the middle? There'll be more at the edge. So do you remember at the outside there, where we're getting lots of melting and things, it slides pretty well. In the very middle of Greenland, that ice doesn't tend to move that fast, and so we don't get it sort of stretched out. We don't get complicated sort of folding of our ice. If we drill an ice core straight down, we should get just nice annual layers. Okay? So I have a really cool little video, because it's all very well to hear this, but it's very different to see it done. And there's a really cool video that I think it's the National Science Foundation made about how we go about drilling our ice. So it's a 5-minute video. Oops.
Of knowledge. Understanding the world we live in to improve our human condition. Today, understanding the Earth's climate is essential to our prosperity. If climate changes significantly, it could impact our ability to grow crops, and shifting weather patterns could also mean dramatic changes to our water supply. But what if we could prepare for those changes? What if we could predict our climate's future by learning about its past? Year after year, our planet records its climate, freezing information into layers of Antarctic ice. And at Waste Divide, a site on the West Antarctic ice sheet selected for its pristine record of climatic changes, scientists are deciphering that information. To do so, they compare greenhouse gas concentrations from the past to temperature data, allowing them to predict how our climate will change in the future based on today's emissions. The wall of a snow pit helps to explain how this process begins. It snows about 2 feet at Waste Divide each year, and it's so cold there that the snow never melts. As it accumulates, the layers compress one another, and eventually the weight of layer upon layer compacts the older snow so much that it becomes solid ice. During this transformation, pockets of air between the snow crystals become trapped as tiny bubbles. A mile or two below the surface of this ice sheet, we find air bubbles that were trapped tens of thousands of years ago, and those bubbles contain samples of the ancient atmosphere. To collect them, scientists use a sophisticated coring drill.
This is the cutter head of our deep ice sheet coring drill. Notice it has 4 razor-sharp cutters on it, and these carve out ice cores buried deep in the ice sheet beneath us.
We send the drill more than 3,000 meters into the ice sheet, and every time we winch it back to the surface, it contains a sample of ice older than the last. We detach the core barrel from the drill and push the samples out into our core handling room next door.
In order to preserve the ice, the core handling room is kept below -20 degrees Celsius. Science technicians record each core's length, temperature, and the date of extraction. And after carefully logging each core, they pack it for shipment to the National Ice Core Laboratory in Denver, Colorado. Waste Divide is an integral part of an extensive research program, but in February, camp begins to close down for the Antarctic winter. Soon, the sun will disappear for more than 3 months, and temperatures will drop below -60 degrees Celsius. The scientists of Waste Divide will return to their universities, where Antarctic ice cores await further analysis. The work done here is only the beginning.
So that's how we get our ice, and because you guys are great and braved the rain, I brought you a present, or Mackenzie brought you a present. We brought you some bits of the Waste Divide and some ice from the South Pole. And so you're going to get to see a bit of the actual ice cores that we come up with, okay? So we'll hand them round. Do you want to?
Sure.
Shall I do this side and you do that side?
That's South Pole.
So this is ice from the South Pole. It's probably a couple of thousand years old. And when you get it, take a look, because you should be able to see, you hold it up to the light, the little bubbles. So see it, but see it quickly because it is melting, okay? So I challenge anyone to make me ice in their freezer that looks like this, because it just doesn't work. The bubbles don't form that way. And so to get those bubbles in the ice, like you can see, it has to be compacted snow. It's never going to form that way if you try and freeze it. We've tried. We can't get it to work. And so that really is that sort of authentic compressed snow that sort of forms over time. So that's really neat. So the waste divide ice you're handling there is probably sort of within the last 10,000 years or something. But there you go, you're holding snow that fell on Antarctica several thousand years ago. And this is what Mackenzie in particular studies. And also Mindy, who's actually sat over in the corner there, she's going to South Pole next year. She's going to be part of the drilling crew, which should be really exciting. She's going to take some videos for me, I think. Okay? So as you sort of get that, do pass it back and get a chance to have a look. And be relatively quick about it, otherwise it's going to melt on us. Okay, so where is that waste divide site? Where is the South Pole site? Here is a little map of Greenland and Antarctica showing where these ice cores are. So you can see that we tend to have them right in the center because that's where we have the thickest ice, that's where it's coldest, we don't have as much movement. The waste divide there is a really interesting site because there's a little bit more sort of dynamics to it. And then you can see also Vostok. Do you remember I mentioned Lake Vostok and how we discovered there was a lake under the really deep ice there, and that's a Russian core site. So it's a really interesting place to be. So we don't just take ice cores from these big ice sheets, though. We also take them from mountain glaciers around the world. And so in the Andes in Africa, we've also called the top of Mount Kilimanjaro, the Himalayas, Alaska, Russia. And these vary because they're not as old necessarily as some of the ice we found elsewhere. They sort of vary from maybe a few hundred to a few thousand years in our mountains, but some can go a little further back. And logistically, we have quite a wonderful support system in Antarctica and Greenland, and those core sites that you saw, if you're drilling 4 kilometers of ice, you can build a pretty permanent site. But in terms of mountain glaciers, you actually have to cart everything up the mountain, and so it really is quite a challenge. The people that do this tend to be quite fit, so they have to carry a lot of equipment around, okay? And recently there's been a real push to try and get cores from a lot of these glaciers because in most places the ice is melting, and so what we want to do is grab these cores as soon as possible so that we don't lose our records, okay? So why do we want so many ice cores? Why can't we just take one from Antarctica and be done? Why do we want lots and lots of ice core records? Sorry? So it's more accurate, absolutely, because if you're a scientist, you want to be able to duplicate your results, right? It's not enough to find it in just one place. If we want to be certain about something, then we really want to see that those patterns are shared between different places. Also, if I want to study climate, am I just going to do that by measuring the temperature in one place? No, we want a network of spots. We want there to be a sort of a large section or sort of a large selection of places, and we can learn something different. We learn something about the local climate in each place we go to. So these have been really helpful to us. So let's think about those 3 different things that we can learn about from our ice. So first of all, thinking back in time, as we've talked about this already, we have that composition of those bubbles that make up the ice. And do you remember this diagram from quite a while ago? Is it looking familiar? So remember, we have that snow falling in the very top, and there's quite a lot of air. It's that sort of nice, fluffy snow. But as it gets compacted, as we get more and more snow on top of it, it basically gets squeezed together. And at a certain point in that fern layer, remember our fern layer, we get so much of sort of pressure squeezing the ice together that those bubbles start to be cut off from the atmosphere around. Okay? So at that point onwards, they're isolated from the atmosphere above, and they keep the same composition. Okay? And underneath that are sort of ice forms. And so, do you remember I asked that really mean question that nobody got right, or at least half people got right and half people got wrong, which is when we think about looking at the chemistry of the ice itself and the composition of the bubbles, remember we're not comparing exactly the same time. And that's because if we look at the chemistry of the ice and the water itself, it's that snow that fell. And by the time we get down here, that's when the bubbles seal off. So if we look down in our fern layer, that snow that makes up the fern actually fell a really long time ago. But the bubbles of atmosphere that are trapped are actually the atmosphere at that particular moment. And in different places, we get different lengths of time before that seals off. And so it snows a lot more on Greenland than it does in parts of Antarctica. So will the age difference between the air bubbles in the ice be greater or smaller on Greenland? What do you think? Okay, let's see if we get a majority answer. Perhaps you might want to think again and talk to your neighbors about it. Think logically. Think about the amount of time. If we get more snow on Greenland, think about the amount of time it would take for that to become ice. Okay, last few votes. So we've had a switch to the other, and hopefully it's because you thought about it rather than just I told you you were wrong. But it is B. So let's think about this for a second, as there's still not a wild swing. Okay. If I'm on Greenland and I get a really big thickness of sort of snow, how many years is it going to take for that snow to form ice? Is it going to take more years or fewer years? Fewer years. So the bubbles that are trapped in that snow as it becomes ice are going to be closer in age to the ice. Oh, right. On Antarctica, if we only get a small amount of snow each year, it's going to take a really, really, really long time for that snow to be compressed to form ice. So the snow will have fallen a really, really long time before the bubbles get sealed off. Does that make sense now? Seeing lots of blank expressions. Is that because you're tired or because you're not following me? Tired. Okay, fair enough. So let's think about the second thing. So that's our composition of our atmosphere. And it's not just CO2 we get. We get things like methane. We get other gases in there that we're interested in. So now we're going to think about air temperature. And it's really amazing that we can do this. And so we're going to talk about isotopes for a while. And this is what my research is in different isotopes. So I'm excited about this. So hopefully, high school chemistry is coming back to you, and you recognize the picture of my nice atom here. So just as a very quick reminder, in the nucleus, in the very center of that atom, we have protons, which have a mass of 1 and a positive charge. We also have neutrons, which also have a mass of 1, but have no charge. And then orbiting around that nucleus, we have electrons. Usually, the same number of electrons that are in the nucleus, unless they've formed bonds with other things. Okay? And so those electrons have a -1 charge, but they don't have a very big mass. They're sort of negligible mass. Okay? So when I talk about isotopes, what I mean is an element that looks like that. And it has the same number of protons and electrons, but it has different numbers of neutrons. Okay? So the positive and negative charges, the protons and electrons balance out. We just add extra neutrally charged things into the nucleus. Okay? And this is important because chemically, it therefore behaves the same, because chemically, something's behavior is controlled by the number of electrons it has. But in terms of the physical properties of that element, it's going to be ever so slightly different. Okay? And that's because one is going to be heavier than the others. So let's take a look at some examples. I think it's easier to think about with some examples. So our air temperatures we get are based on oxygen isotopes. And we like oxygen because it's in H2O, so it's in our ice. And we have 3 types of oxygen. We have 3 isotopes. We have 16, we have 17, and we have 18. And so that 16, 17, 18 represents the mass. Okay? So in our 16 oxygen, which makes up 99.76% of the oxygen that exists in the world today, we have 8 protons, 8 neutrons. Okay, so its mass adds up to 16. What would we have in 17 oxygen? How many protons would we have? 8. So how many neutrons would we have? So obvious answer of the day. In oxygen 18, how many protons would we have? 8 still. So how many neutrons would we have to have? 10. Okay, so it's as simple as that. It's really not any more complicated than that. And in particular, we're going to ignore oxygen 17. So they're in really small amounts. We're instead going to look at oxygen 16 and oxygen 18. So we can ignore that one. And when we use sort of notation to describe the ratio of oxygen 18 to oxygen 16, we use this funny symbol, this delta symbol. Okay? So what I'm talking about when I use delta O18, I'm talking about the ratio of oxygen 18 over oxygen 16. Okay? Close enough. So I said that chemically they behave the same. So they form the same chemical bonds. They still form calcium carbonate. They still form water. Okay? But physically, having the different isotopes makes a difference because one of them is heavier than the other. And so in physical processes, things like evaporation, condensation, they behave ever so slightly differently. So here's my ocean. It is a mixture of that oxygen 16 and oxygen 18. Which of those two do you think it's going to be easier to evaporate? Was it going to be water with oxygen 16 or water with oxygen 18? Oxygen 16, why? It's lighter, so it's going to take less energy. So as we have evaporation, we have what we call fractionation, which is just we leave behind the heavier oxygen 18, and in the atmosphere we end up with more water vapor containing oxygen 16. Okay. So that lighter oxygen 16 in the water molecule means that it evaporates more easily. So our clouds tend to have more oxygen 16 in them. And those clouds tend to move towards the pole. We have lots of evaporation happening over warm areas of our ocean, and then that tends to move towards our pole. As it moves towards the pole, we get sort of colder and colder, and so we get more of that water vapor condensing out, and we get rainfall. What do you think is going to be more likely to fall out of our sort of cloud? Is it going to be water containing oxygen 16 or water containing oxygen 18? 18, why? Because it's heavier, okay. So these aren't too complicated to think about. So the rainfall that comes out of those clouds is going to have a little bit more water with oxygen 18 compared to water with oxygen 16. And so what that does to our cloud is it makes it even more oxygen 16 rich. Okay? So as this process goes on, as it moves towards the pole, we just get more and more and more water with oxygen 16 making up our clouds. Okay? So by the time it reaches the poles, things like Greenland, places like Antarctica, and we get snowfall there, is there going to be lots of oxygen 16 in that snowfall or lots of oxygen 18? Lots of oxygen 16, absolutely. Okay? So it snows there, and that ice, which has got lots and lots of oxygen 16 in it, builds up. Does that make sense, or do you want me to do it one more time? One more time? Okay. So let's go backwards in time. So my ocean has a mixture of water containing oxygen 16 and water containing oxygen 18. And if we're going to have evaporation, it's going to be easier to evaporate that water containing the oxygen 16 because it's lighter. Okay? And so that water containing oxygen 16 goes into the atmosphere, and that water vapor eventually condenses and forms our clouds. Those clouds move towards the poles. Okay? And as they move towards the poles, it gets colder, we get more condensation, we get rainfall coming out of those clouds. And if we're going to have condensation and rain falling out of the clouds, then that rain actually contains a little bit more oxygen 18 because it's heavier, it's going to condense more easily, okay? And that means that by the time we get up to the pole, those clouds have a huge amount of oxygen 16 in them compared to the oxygen 18. And so the snowfall that they produce has a lot more oxygen 16 than oxygen 18 in them. And that's the snow that goes into building up our ice. So if we were to measure the ratio of the ice that I handed around, it would have a huge amount of oxygen 16 in it compared to oxygen 18. And what we call that is a more negative delta O18. Okay? So if it's a more positive delta O18, it has more 18 oxygen. If it has more 16, then it's a more negative delta O18. Okay? Might take a couple of times to think about it. You can write this out yourself over the weekend. So, the really neat thing is that if we go and we measure that ratio of oxygen 16 to oxygen 18 in the rainfall at different latitudes, it almost perfectly, but it amazingly well matches up with the average annual temperature. You don't often see a scientific graph that looks quite as neat as this, okay? So along my x-axis here at the bottom, I have the mean annual temperature in degrees Celsius, and then up the side, I have that delta O18 of the rainfall or snowfall, whatever's coming out of the sky, okay? You can see that it forms a really nice straight line. And so what that means is that if someone were to sort of go out and go on holiday and bring me back a little sort of a vial full of rainwater that they collected, then I would be able to go and measure that O18, and I would be able to tell them what the average annual temperature was at the place they went. Okay? So it's a very neat thing. So let's put this into practice. So I have a two-part iClicker question. Okay? So the first part is I want you to look at this graph, which is the delta O18 record of an ice core from Antarctica, the Bird ice core. And I want you to look. So it goes from 60,000 years ago to 30,000 years ago. Look at what the sort of range in the delta O18 is, and write that down because you'll need it for the second part. Okay? So what's the minimum and maximum delta O18 value? Has everyone got that? Okay, so hopefully everyone has the minimum and maximum. So now your challenge is use those minimum and maximum to work out the coldest and the warmest temperatures that were experienced at that particular site. So what is the range? What's the difference between the maximum and minimum that was experienced at this particular ice core site on Antarctica? So you can consult your neighbor if you'd like. Consult the TAs. So I think that's more or less everyone. So put in your vote if you haven't had a chance to. You sure? Okay. Maybe I'm doing it wrong. Okay, hang on a sec. I might be doing it wrong. So let's have a look. So what is the maximum of the delta O18? Maybe minus 37 or so, 38. What's the minimum? Minus 41. So let's move forward. So minus 41 would be about here-ish. Okay, if we go across and we read down, it would maybe be minus 40. Oh, hang on, I am doing it wrong. There you go. And then we go to minus 37, which is probably about there-ish. Okay, we go across here. So I'm so sorry, guys. You're absolutely right. I think I wrote the I wrote the quiz last night, and there's basically an identical one. So now you know it's not 5 degrees on the quiz, at least. So yes, you are right. Does that make sense to those of you that voted for the different one? Yes? Thank you. Well done, guys. So let's think about what else we can do. So that's how we look at the temperature record of our ice cores. So it really is as simple as that delta O18 of the rainfall or the snowfall just corresponds really nicely to your average annual temperature. And so if we can go into our ice core and measure the difference in the delta O18 in the ice, then we can get a sense of how temperature is changing. And that's really cool for us because we can also pair that with our record of how the atmosphere is changing. And so this is really the most important sort of information that we had to tell us that if we're going to massively change the amount of carbon dioxide in our atmosphere, then we're also probably going to see a change in our temperature. We can also use oxygen isotopes within the ocean in order to get a sense for how much ice there is on Earth. So here it looks probably very familiar looking diagrams. And so the nice thing about looking at oxygen isotopes is that there's oxygen in a huge number of things. So in particular, in the ocean, we can look at shells, which are made of calcium carbonate, and you can see that we have oxygen in there. So what we can do is, by looking at what the ocean delta O18 is, which is preserved in these nice calcium carbonate shells, we can get a sense of how much ice is on the continent compared to how much water is in the ocean. Okay? So I have my warm climate at the top. I have my cold climate at the bottom there. Okay? And what I want you to tell me is, during a colder period on Earth, will the ocean contain more or less O18 than during warmer periods? Okay? So I'm going to give you a couple of minutes to think about it. Consult your neighbor again. So during a colder period, will there be more or less O18 in our oceans? Okay, I think that's more or less everyone. So let's see how we did with this one. 60-40 split again. Turn to the people behind you and tell them what you think. There's a logic here, and look at the diagrams. The diagrams also give you a big indication. Okay, so put in your votes for those of you that haven't yet. Missing a few. Okay, so let's see if the people behind you were any help. No, none at all, it looks like. So, if you look at my little diagram, what does it say in the bottom here? The oxygen 16 is trapped in the ice. So how much is the ocean going to have more or less oxygen 18? Would it? Oh, okay. I think I might know what the problem is here. If I change this to oxygen 16, is that any easier? No? Okay. Fair enough. Okay, so let's think about this. In my warm climate, I have evaporation. That oxygen 16 is getting into my atmosphere. It's traveling and it's raining out. But as it rains out, it doesn't build up on land. It just runs straight back into the ocean again. Okay? So my ratio of oxygen 16 to oxygen 18 is there's going to be more oxygen 16 in the ocean. Okay? In my cold climate, I have lots of oxygen 16 getting evaporated, and it's going into my atmosphere, and then it travels to the pole, and that falls as ice. And instead of running back into the ocean, that water, which contains lots and lots of oxygen 16, is piled up on land. Okay? So we end up with less and less oxygen 16 in my ocean, and so in terms of that ratio, we have sort of more oxygen 18 compared to the oxygen 16. Okay? So at the top, in my warm climate, I have seawater with sort of light and heavy isotopes. But during my cold climate, when I have more of that light oxygen piled up on land, my ocean contains sort of proportionally more of that heavy oxygen. Does that make sense now? Yeah? Okay. This, in general, isotopes take a little bit of thinking about. There's a lot of logical steps to the process. And so it may be something that you have to sort of take some time and write down. This is what's happening, so this leads to this, so this leads to this. But usually it does end up making sense. So let's quickly move on to looking at what else we can look at. So we've done composition of the atmosphere, we've looked at our air temperature, but we can also get records of the particles in the atmosphere. And in particular, this is what Mackenzie does. She looks at signals of forest fires from the chemical compounds that are found in the ice. So we can find out a number of things. We can find out sort of how much ash there was in the atmosphere at different times due to volcanic eruptions. We can find out how much dust and sea salt there is, which indicates how dry and dusty or how windy conditions were. We can find sort of soot from large forest fires, so we might be able to identify, especially in mountain glaciers, when there were periods of heavier forest fire activity. And also, in particular, for the last 2,000 years or so, we can see really clear signals of human pollution. And in particular, if you go to the Waste Divide, I think, you can even see the point where the Clean Air Act was enacted in the US, because we go from having lots of sort of lead to having very little above, which is really neat. And the whole actually color of the ice changes at that point. So the nice thing is we can get this amazing record, but it's all very well having the air temperature, the composition of the air, and dust, but we also need to know when, right? It's no point knowing how something changes if we don't know when it changes. Because without knowing when it changes, we can't really say anything conclusive about why it changes. Okay? So we need to somehow construct a time scale for our ice core. So does anyone have any ideas how we might go about doing that? Wow, this guy at the front, give him a gold star if we were in primary school. But yes, we can match up volcanic eruptions, because if we have really big volcanic eruptions that put amazing amounts of ash into the atmosphere, and that goes worldwide, we can actually sort of match up our different ice cores in different places and sort of match them together. From my image here, which might give you a clue, what other way might we be able to construct a time scale? Layers. We have actually annual layers. So these little sort of stripes you can see in the ice there are annual layers. Okay? So we can actually count back the annual layers in the ice. And definitely as that ice gets older, it gets much more compressed, and it's difficult to do that. But there are people that spend their time sort of counting the annual layers to give us our time scale. Okay? And so what do you think happens to our sort of level of uncertainty as we go further back in time? It increases because those errors sort of add up as we go back. And so it's a really big challenge working out our time scale. So eruptions are a really nice tie point that help us check on our consistency. So we have all of these lovely things. What do they show us? So here is a pretty amazing record of the Antarctic ice core, and it goes back to 800,000 years ago. Isn't that amazing? So we have an 800,000 year record of climate in terms of things like the carbon dioxide concentration, the methane concentration, the nitrogen or the nitrous oxide concentration. We have temperature there in the blue. We have the amount of dust in the purple at the bottom. And then at the very top there, we have those Milankovitch cycles. Okay? So for this particular latitude, what is the Milankovitch cycle doing? Okay? So does anyone want to tell me what they observe? There are lots of things to observe. Give me one observation. Is it a perfectly flat line? No. What does it do? It spikes. And in particular, how often does it spike? Every 100,000 years. Does that sound familiar? Milankovitch cycles. We're coming back to this idea again, okay? What else do you notice about how these little different information from the ice core lines up? So when we see the highest temperature, what do we see in terms of the CO2? Yeah, absolutely. So the temperature and the CO2 records seem to match up pretty well. When one's high, the other's high. When is it driest? During the warm phases or the cold phases? Come on, I know it's Friday and it's nearly the weekend, but you can do this. Who votes warm? Who votes dry? Oh, hang on. I'm sorry, I need sleep as well. Who votes cold, rather? Okay, enough. Okay, yeah, absolutely, it's cold. So it's also dry when it's cold, absolutely. So why might it be dry when it's cold? There you go, answer me that question. There's less moisture, absolutely. So do you remember we said that now that our world is warming ever so slightly, we're getting more moisture in a lot of places. The same goes for the past. If it was much colder, then we have less moisture in the atmosphere on average. So the last glacial was a really quite dry, dusty time, and that's what we tend to see. We can see that that sort of amount of dust builds up and builds up. And so that's sort of our sort of coldest point when we have that really dusty spike there. Okay, so we can sort of start to see patterns, and we can start to work out what our climate is doing. And so here's a really interesting comparison. Okay, this is a comparison between the Greenland ice core for just the last 50,000 years or so, and the Antarctic ice core for the last 50,000 years. So Greenland is in red, and Antarctic ice core is in blue. What on earth is going on? It's doing some crazy stuff, right? So if you're a scientist and you're looking at that, you go, oh no, what have I done wrong? Okay? But it isn't, it's actually what happened. So you can see that this is why I was confused, because those temperature swings that we see in the Greenland ice core are enormous. They're really enormous compared to the change that we see in Greenland. You can also see that those really big swings in temperature don't seem to happen in the last 10,000 years or so when it's warmer. Right? Does anyone know where I'm going with this? Not quite yet? Okay. So something is happening around Greenland that isn't happening around Antarctica. It also only happens when we have lots and lots of ice around Greenland. Okay? And it's not related to CO2, but CO2 is changing in both places at the same time. Does anyone know what we might be talking about? This again? Our day after tomorrow scenario. This is how we found out about this, okay? These enormous swings, we drilled this core, and we weren't expecting anything like this. And we went, oh my goodness, what is going on? And this sort of finally sort of showed us that we saw this amazing sort of sensitivity of the thermo-hairline circulation. So do you remember we have this sort of circulation that involves the whole ocean, okay? It starts off with really dense water, that cold, salty water in the North Atlantic sinking. And it doesn't just sink a bit, it sinks all the way down to 4 kilometers down. And then it runs along the bottom of the North Atlantic. It runs along the bottom of the Southern Ocean. It comes up a little bit in the Indian Ocean. It runs up through the North Pacific and then comes to the surface again. Does anyone know how long it takes to do that? About 1,500 years maybe. So it's really old water coming to the surface, and then it flows round again, okay? And so what happens is that you can see how our Gulf Stream there is being pulled really far north by the sinking of that deep water. If we didn't have that deep water sinking, then we wouldn't pull that Gulf Stream so far north. It would instead sort of head back round, maybe around sort of Spain, and disappear off, okay? So let's think about what else we see. So at the same time, we see those massive swings in temperature in the ice core record. If we go out and we look at sediment cores from the deep ocean in the Atlantic, we also see pretty big grains of sand, and even a little bit bigger than sand. So remembering our last lecture, where might they have come from? Icebergs. Do you remember we had drop stones? We had those icebergs that were drop stones. And this is where that sand came from. At the same time we see these massive swings in temperature, we see these sort of little bits of sand in our North Atlantic. And so the idea is that when we had these enormous ice sheets on North America around Europe, then every now and again we'd have enormous sort of armadas of icebergs sort of floating out into the North Atlantic. And they melted and they dropped that sediment to the base. And they also released a lot of fresh water into the North Atlantic. And that prevented that deep water forming. And that basically turned off our thermo-hairline circulation for a while. And that stops that heat being transported up to the North Atlantic around Europe, okay? So, and that's what this sort of film was based on, this day after tomorrow scenario, okay? And so we talked about that. So could that happen? Give me one more minute. So could that happen today? Because that's our concern. If we went back to the 1970s, people would say, are we about to enter a new ice age because of this? And in reality, if we look at how much fresh water there is today, we just don't have enough coming off our Greenland ice sheet to really make a huge difference. But what we are expecting, or what is forecast, is for a reduction in the strength of that circulation. Okay, it's not going to save Europe from further warming due to increased greenhouse gases, but it might mean that there's a little less warming there than elsewhere. Okay, so don't buy snowshoes just yet, which should be fine. Okay, thanks guys.